Welcome. Last week I got this beautiful book of Oliver Byrne. It's an illustrated version of Euclid's Elements. Very beautiful diagrams, colorful diagrams. It's a prototype how to make mathematics more accessible. And I thought about doing that for finite geometry, simplicial complexes in particular, which are a little bit abstract because it's set theory, right? Sets of sets, finite set of non-empty sets closed to the operation of taking finite non-empty subsets. So we have also the notion of Euler characteristic, which is very important. There are many theorems about this. And Euler characteristic, I like to think about linear characteristic. It's a sum of energies of simplices, positive energies for even-dimensional simplices and negative energies for odd-dimensional simplices. Now, there's a quadratic version, interacting simplices. If two simplices intersect, then you can look at their common energy, which is the product omega x times omega y. And you can add that up. That's I call that Wu characteristic. It's a quadratic characteristic. There are higher characteristic, cubic characteristic for m equal to 3, m equal to 4. So you can look at that for any number of interacting simplices. Very interesting notion. I worked on this for almost 10 years now, and there is a cohomology, there are theorems. Essentially any theorem which you can think of works nicely also there. For example, there's a Lefschetz fixed point theorem, which, so if you have an action map on the simplicial complex, and you can look at the fixed points, and you can look at the supertrace on cohomology, which is the Lefschetz number, and that generalizes the Euler-Poincaré formula. So there is a cohomology, there are Betti numbers. And I also looked at this in the context of topology, because we can look at cohomology of open sets and closed sets, and you can look at how they interact. And that's especially interesting in the higher characteristic version, because simplices from different parts can interact. So I talked about this for many, many times here already, especially last year. There is a fusion inequality for just a pair of open and closed set, and there is also a quadratic fusion inequality, which is more complicated because now different parts can interact. But I want to go back much just to the very beginning and actually just illustrate that this notion, that one appreciates that this notion is not, so obvious. And especially this, what I call proposition 6 in the last talk, right? This is this local valuation property, which says that for m odd, like for Euler characteristic, we have a valuation property that the open set and closed set add together nicely. And in the case of even dimension or even characteristic, like quadratic characteristic, it's a minus sign. And that's what I want to illustrate in the simplest examples. Maybe also I got into that again because of this result that all these higher characteristics agree on the Sommerville spaces, which are manifolds. Manifolds, you don't have, there's nothing different, but it's different if you have, for example, manifolds with boundary. It's just the Euler characteristic minus the Euler characteristic of the boundary. And very interesting is the cohomology, which is highly non-trivial because the space in another space interacts in a nice way, and I want to compute much more there. Like we have seen that the Möbius strip can be distinguished from the cylinder just cohomologically by looking at this quadratic cohomology, which is a simple example, but you can do hopefully much more, like maybe distinguishing knots just by looking at cohomology. So that's this. So there's a little bit of topology. Maybe kind of these examples illustrate the framework. So what we have is a finite set of sets I have two examples, kind of the K2 and K3, the simplest examples which you can think about. And the first case, we have three sets, right? We have a point to the left, a vertex to the left, a vertex to the right, and then a connection between them. And now we can look at the star of simplex. Let's take the simplex, which is just a point 1, and look at the star, which are all the sets which contain this. This is, I call this the comma space, right? It has a point and an edge, so there are only 2 points. And then there is the boundary of the closure, which is, I call this the unit sphere. It's the most natural notion, some call it the link, but it's the most obvious thing you can do. You have the smallest open set, and then you look at the boundary. How do you take the boundary? Of course, you take the closure, smallest simplicity complex which contains it, and then you take the interior away. So that's like, it's topology, it's nothing else than classical topology. And so what we have is then the unit sphere. And then we have this proposition 6, which tells us how, the characteristic, the higher characteristics of this open ball, and this is here the open ball, and the higher characteristic of the unit sphere, in this case the unit sphere is just one single point, relate to the Euler characteristic or the higher characteristic, quadratic characteristic in particular, of the ball, of the closed ball, which is here the whole space. So let's look at here the case of the unit ball of 1, right? It's the smallest simplicity complex which contains the open set Ux, and which is of course then just the K2, which is the whole space in this case. And now we can look at interacting simplices. So we can look at the interaction of zero-dimensional simplices. These are these two examples. They have to intersect, so they have to be at the same point. There are two cases. They are positive because the omega x is positive for a point. And in this case, there are negative cases. There are interactions of the edge with the points. So in this case, we have 1, 2, 3, 4 interactions which give us a negative value because the edge has negative energy and the vertex has positive energy. And then to the very end, we have the interaction of the edges. Of course, that gives us energy 1 because both edges have energy -1. So in this case, we have 7 interactive parts, and they all add up to -1. So this K2 has characteristic -1. So that's the first thing you're doing. You investigate what happens actually with the simplices, what happens with, Kn. And so it's just -1 to the n for even characteristic, a quadratic characteristic, and it's always 1 for odd, like the Euler characteristic. All the simplices have Euler characteristic 1. That's a small combinatorial exercise to check that for in general. But here is the case of the open ball, the star. If you look at the star, kind of the atoms of space, right, these open sets, these smallest open sets, they have a characteristic 0. So in this case, we have 4 interactive parts, and 2 of them are positive, 2 of them are negative. But the positive parts, if you have 2 points, and here 2 edges, and here, these are the cases when we have a point and an edge interacting. So this is 0. And in this case, when we have just the unit sphere, it's actually just a single point. In this case, they are just zero-dimensional simplices, and of course there's just 1. So the characteristic is 1. So that's the example, and we see kind of this proposition 6, right? We see this work in the case of a very small space and m equal to 2. In the case of m equal to 1, Euler characteristic, then what happens is the Euler characteristic, if this is 0, because we have 1 edge and 1 vertex, right? So 1 plus -1 gives 0. In this case it's 1, in this case it's 1, so it's also the case here. Now, just to appreciate this, we can look at the triangle. So in the triangle, that's a simplicial complex with 7 elements, right? 7 sets, 7 non-empty finite sets. And here is kind of the picture. It's also the unit ball of one of the vertices if you want. And so what we have is the, we take a vertex and we take the open set. This is the star. Right? These are all the sets which contain 1. So it's 1, 1, 2, 1, 3, 1, 2, 3. And we can now look at the unit sphere. The unit sphere R is the closure minus the u of x. It's a boundary. In this case, this is just this missing part here. So that's the unit sphere. And now we can look at, in each case, we can look at the second or the quadratic characteristic. So what happens in the case of the whole space that has already 37 interacting simplices. So we have 49 in total, right? But not all interact. Like for example, if you take a vertex here and an edge here, they don't interact. So there are some of them which are not participating in this quadratic characteristic, but 37 of them do. And what I did here is just, painfully just listed up all the possible cases of interactions. So we have interactions between vertices, we have interactions between vertices and edges, we have interactions between vertices and triangles, and we have interactions between triangles, we have interactions between triangles and edges, and so on. So there are all the possibilities, and we can look at that all together. Together it gives us just 1. That's the quadratic characteristic of the triangle. Now again, we can look at the open set of the point. This is the open set, right? It contains, I didn't actually write it. Oh, here I wrote it down. Right? The open set 1, 1, 2, 1, 3, 1, 2, 3. These are all the sets which contain 1. That's the star of the simplex 1. And we have, again, we can just look at all the cases which occur. So in this case, there are 8 cases with positive energy, 8 cases with negative interaction energy. Total is 0. So that's the quadratic characteristic of this open set. The unit sphere, we can go back to what we did already. What we did here, we have actually seen it's -1. By the way, like this, you can go inductively higher and higher. You can look at then the next step would be the K4, which is the tetrahedron, and then you go higher, and so you can look at that. Now, but this theorem is here, this proposition is much more general. S of x can be an arbitrary simplicial complex, for example. Then you take the cone extension, you would get the cone extension of that simplicial complex, and that's the open set. This is a very, very kind of already quite a general thing, even so it looks normal. It looks local. I think that's what I wanted to say today.